Welcome, everybody, to the second class, CPSC 323. This is the first time we'll be taking attendance. Very easy to sign your name. Pass it around. So, last time we talked about what does it mean for a machine to think. Now, we try to separate different parts of what thinking is, or define what thinking is. It could just be a word, like we can make it mean whatever we want. Like we change the definition of planet, so Pluto is no longer a planet. Why? So like to call it a planet. I mean, it's very round. It's got a big heart on the side. It loves us. So why not call it a planet? But we can define thinking however we want. So if thinking is something that computers maybe can do, what else is there going on in your brain that computers definitely cannot do? Name one thing going on in your mind. Feel emotions, yes. Feel, that's the important part, the feeling. You can have a computer act as if it has emotions. And we're thinking about something as simple as suffering. Is there any computer that has ever suffered? If it does, then you would have a responsibility to make it not suffer, right? Well, we're not going to do that because we can't do that yet. We're going to talk about just thinking in terms of processing information. If you know something, quote unquote, know, that means it has been registered somewhere in the computer. A knowledge representation scheme was chosen and bits were stored using that scheme. Now, this is from one of my favorite movies. This is where I was introduced to machine learning, all the way back in 1983. And machine learning here is a certain kind of information processing. There's this computer, this Professor Falcon, not pictured there, that's one of his assistants, said he designed this computer so that it could learn from its own mistakes. So that better the next time they played, the system actually learned how to learn. It could teach itself. Even when machine learning became a real thing in the 90s, this was still very hard to do. Now, some people believe that certain kinds of feedback systems can do this right now. We will cover them at some point in class. But this is still kind of new. But what I love about this is all the way back in 1983, the writers for this movie had some of the key concepts in place. They had this idea, okay, this computer is learning how to play blackjack or something. And you have different options, deal, hit, stay. And when the computer lost, that was input. This is supervised training. In supervised training, the computer tries to come up with a guess. When it gets it right, it's rewarded. When it gets it wrong, it's punished. Or there's a loss function, say. That's supervised training. Could there be any other kind? Is there such a thing as unsupervised? How would that work?
You did a bunch of like pictures, like the pictures of things, like let's say a dog, and then you classify them as dog to the computer, and then you feed them cats and say this is a cat or this is not a dog, and then eventually like it'll process that data, and then it'll tell you based on its prediction if it's the accuracy it's dog.
But if you're telling it's a dog or telling it's a cat, that's the supervision. Unsupervised means you're not telling anything. How on earth can it learn? You don't tell it what it's supposed to learn. You can just think about that one. We'll get to that later in the course. Today, we're going to talk about the basics of what machine learning is and what it's not. Machine learning is not human-designed computation. That's the conventional way to program. A programmer thinks through a problem, comes up with pieces of the problem, how to solve it, write it down, and you solve it. Free. That's not machine learning. Machine learning is not singularity. Who's heard of the singularity? Yeah, so I've met some people who believe 100% it's coming, and we're going to be left behind. How would you describe the singularity?
Isn't it more like AI is essentially take over? I don't know, there's somewhere like we were computers, so we like put ourselves, but kind of robotic words.
Yeah, there's a lot of ways to describe it. One of the ways that I think about it, which I believe is possible, is there will become a point where technology starts progressing faster than our aggregate ability to understand. So right now, whenever something progresses, there's always some PhD candidate somewhere in the world that understands what he did, right? So there's someone in the world who understands that progress. But there will come a point when technology will progress itself faster than anybody's ability to understand. Now think about this. If some country in the world is able to create a virtual Einstein, what can you do with a virtual Einstein? Imagine it can think and do internet searches and computations and everything that Einstein did. What would you do if you had a virtual Einstein?
I guess it's like propose the world's current problems. That's like how it gets through them.
Yeah. And let's pretend you told him, okay, go do 10,000 years of research on fusion. Then 5 seconds later it comes back. I just finished 10,000 years of research. Because computers can process so much faster, it could simulate Einstein faster than the real Einstein could live. If a country had this, would any other country's technology be able to catch up? Whoever gets there first, there's no point in second place. There's pretty high stakes here. But what we're going to talk about in this course is not the singularity, and it's not true artificial intelligence. It's not general human intelligence. And it's not cyber beings replacing humans. But some things about us will be replaced by machine learning. Give me some examples. Some examples of jobs that will be replaced very soon by machine learning. Delivery trucks? Yes. But probably the long haul truckers first. Being in a city, backing up into a small alleyway is still very hard for AI. But the highway drivers, they can be great, they can do better than humans. What's another one? Manufacturing. Manufacturing, yes. So that started in the 80s with robots and plants, right? In car plants. Cooking. How is cooking going to be replaced by AI?
Here I think about a bunch of recipes, upload them to the robot and automatically make it.
Yeah. There's a restaurant I didn't feel like going into in San Francisco. I think it's called Eat Lean. And EAT.ly, something like that. No humans working in there. You go in, you order something, the robot puts it together, and then this chamber opens so you can get your meal. But yeah, it's coming. Will the blue collar jobs go away first or the white collar jobs? Let's give it a show of hands. Who thinks the white collar jobs will go away first? Who thinks the blue collar jobs will go away first? All right, I think the white collar jobs will go away first. Here's why. Blue collar jobs involve many things that are way harder Like going into a basement and adjusting pipes is a plumber. Or taking out a part of drywall, and doing the electrician work again, bringing up the code. That is all really hard for an AI. But things like being a radiologist or making economic policy or deciding in a given court case whether a person is likely to reoffend. We have all actually had better success on those types of questions with AI. Now, Tesla famously announced we're going to have lights out factories, the machine that makes the machine. We're going to have this giant factory with no humans working in it. It didn't work out for them. There are some jobs they have the AI doing now, the robots, and other jobs that humans do, and they probably always will be as far as they're concerned. Can you guess what kind of jobs they have to have humans do? No, but maybe they do for that. But that's not what I've heard. What I've heard is that the dividing line is if everything is rigid and stiff, like steel components, hard plastic, the robots and AI do great, and they do better. But if you have cloth with the seats, bundles of wire, anything that's flexible, humans do way better. Now, what's the danger if you have humans and robots working together? What's one of the dangers they came across, do you think? Spatial awareness. Yes. Spatial awareness. Is that what you were going to say?
Let's say the robot doesn't know to stop.
Yeah.
So,
Yeah. Giant, super strong, multi-ton machine moving this way, and you happen to be in the way. It could be problems. But they've worked on that. Okay, machine learning is computer designated computation instead of human designated. It is finding patterns. Now, we all can find patterns. Humans are great at finding patterns. We're so good at finding patterns that we find patterns even when they're not there. Like, have you ever seen something in a cloud? Like it looks like a puppy dog or dragon or something. Obviously, it's not a real puppy dog. Your brain found a pattern. I don't know if you know this, but every time you see the front of a car, the neurons in your brain responsible for facial recognition are activated. Brain is repurposing facial recognition for front of car recognition. So that moving cars actually makes sense. However, I would not have put the eyes on the windshield. I think that's a mistake. Using patterns to make predictions. When I said radiologist, someone who looks at scans and decides if you have cancer, if your tumor is malignant or benign, that's a prediction made from patterns. There are patterns that computers can see that we absolutely cannot. And I'll give you an example. A friend of mine at the University of Maine was studying, using computers to study images of tumors and decide if they were, benign or malignant through machine learning. And it's all about finding the right features. What's a feature? When I say features of machine learning, I want to hear from someone who hasn't spoken before.
It's like an attribute.
Yeah, an attribute. Like if you have a scan and you've got, a bunch of tissue in here, whatever, and then somewhere in here is a mass. What are some of the attributes or features of that mass? Throw out some words. What do you say? The radius, good, very good. What else?
Color.
Color. What else? Surface area, yes. Density, great. Yeah, those are all great things. Let's talk about surface. Now, if this is a two-dimensional image, really we have a one-dimensional, surface here, right? Around this two-dimensional region. This is the one feature that this guy was focused on. Andre Khalil is his name. And he was interested in mathematical ways to describe that feature. And one thing that comes up is the Hurst exponent. Now I'm getting into some weeds here, but I'm just giving you an example that I think you'll remember that helps you remember we got to look for features. Sometimes you can let the computer find the features on its own. Other times you do feature engineering, where you get that feature and maybe you normalize it or you process it mathematically to make it work. And this is what he did. So the Hurst exponent is actually a measure of the roughness. And it comes from fractal geometry. So one example of a fractal would be you have, some line, you divide it into thirds, leave one blank, and then do that again, and do that again, do that again on forever. Now, if you were to look at it at the big scale and look at it at this scale, it's the same shape. It's exactly the same as it goes on forever. Well, if you look at any one-dimensional time sequence, for instance, or any one-dimensional sequence, there sometimes is a fractality to it. And what he discovered is that there are fractal consistencies within this surface around tumors. And he can use another kind of math called wavelet decomposition to estimate the Hurst exponent, which is just the roughness, but it's a fractal roughness. And what he found is that when he had the machine look at a whole lot of scans, and he knew, because we were doing supervised training, he knew which ones were benign, which ones were malignant. If you have a Hurst exponents, I can't remember the numbers, but it was some kind of range in which they were all malignant in this range, and they were benign outside of it. And I'm just going to take a wild guess that it was between 1.3 and 3, something like this. And this already was a great discovery and awesome. Now, after he was working on this, like a year later, some deep learning guys came up with their own model for tumor classification, and it was more accurate than his. So that's what the industry went with. But at the time, this was really an amazing result. But the thing that blew me away the most was that there was this other researcher he met at a conference who was studying just the temperature. Remember, another feature. So this other guy was studying the temperature of tumors as a time series. And then he was calculating the Hurst exponent of that time series of temperature. And he found, again, between something like 1.3 and 3, whatever the numbers were, it was the same numbers. He found that it was malignant in here and benign outside. And I think that's mind-blowing. But these are the kinds of patterns that a human working together with machine learning can find as you go along. Eventually, we'll get to a point where there are patterns that a human can't even understand after you've found them and are using them. That's more complex, and we'll get there later. Okay, conventional programming. A programmer has an idea in his head. He programs the computer to do that thing. He gets some input, and then he gets them out. Machine learning is more like programming something else that then programs the computer. So when I do machine learning, I get a whole bunch of data and I tell my software, try to learn from the data. And then it learns from the data, and then this other computer, in a sense, smart program, whatever, it decides what the numbers and values in the resulting final program will be. So conventional program, you have to program the computer. But in machine learning, in effect, you're programming something to program the computer. Okay, now let's talk about your first homework. You're gonna start it today when you run home from class and you're so excited to get homework started. And it's gonna be the easiest one all semester. It'll be fun. And it's gonna get you used to the pattern. So every homework assignment is gonna be done as a notebook, a Python notebook on Google Drive. Is there anyone here who's never done a Python notebook before? All right, this is your first time. There's a lot of tutorials online. Just open up one. What's great about Google Drive specifically is that when you have a notebook file in there, double click it and it automatically opens up Google Colab, which is how you can run Python for free using Google's computers. And I highly suggest you do that. Of course, you've got many other resources available to you at the university here, but this will suffice you for the class. Also, when I go to correct your homework, I will double click on that same IPNYB file, and it will open up Google Colab for me, and it will open it up in the state you left it in. So if you run a bunch of stuff and you have your results at the end, I will be able to see those results. And I might even make comments in there. Okay, your first homework is you need to find a skewed data set. Now, for a description of what you're going to do, typically you would start off in the right folder. Now, if you go to the syllabus, you'll see here a folder for the projects. When it says projects, these are your homeworks. Remember, there's no midterm, there's no final, just your projects. And you may have noticed somewhere in here, there will be an oral presentation. Every one of you will give an oral presentation, 5 to 10 minutes. It's easy and it's more fun than you think. And it has to be on something in machine learning or AI that we did not discuss in class. So if you wait to the end, we will probably discuss everything and there'll be nothing else for you to talk about. Yes, we can do it right now if you want. But at the end, if not enough people do it, we're going to be using it the last couple of classes just to go through you all. So I highly suggest you start thinking about it and get on the calendar, talk to me. Otherwise, eventually I put you on the calendar. And that's 10% of your grade. The being present in class and class participation is another 10%, but 80% of these projects. Okay, so let's go to that projects directory. When you do, you get this. The project directory is labeled with the due date. That is a Thursday. So every time you come to class on Thursday, you get a new project at the end of class. This, of course, doesn't apply for Thanksgiving. And it will be due on September 8th. So before midnight, September 8th, but it's probably a good pattern to get it done before you come to class. Okay, now if we go in there, you will see there is a README file. This README file has everything you need to know for that homework. This first one is called the dumb predictor. So one time I was building a model on a very skewed data set. I don't remember what it was, but it wasn't this, but it was similar to fraud detection. I give the example of fraud detection. 99.99% of all transactions on the credit card systems in America are not fraud, but 0.001% are. So if you build a fraud detection algorithm and it's 99.99% accurate, is it worth anything at all? It could be totally worthless. In fact, you can create a fraud detection algorithm that's 99.99% accurate by merely outputting, not fraud, every time. It doesn't even look at the data, it ignores it. And that's actually what I want you to do for the first project. You have to go out in the world, find your own data set. A data set that's skewed, meaning it's almost entirely one thing. And you're going to just predict it's that. But what you're going to learn in this process is how to get a data set, save in the right place, or load it in the right way. Bring it in, read it in. You have to actually have it load into some kind of vector or input or text or something. Pass that to your model. Now for the model, you need to create a Python object. It's called class, and it's going to have an init function. And the init function is just something you have to define for every Python object. But more importantly, it's going to have a predict function or method. Just predict. And you're going to feed it a whole bunch of inputs at once. And the reason you're doing it this way is because this is how scikit-learn does it, and how a lot of other machine learning systems just tend to do it. So in your code somewhere, you have, class, model. If it were based on something like a subclass of something, you would put that in there. You would have some init, and maybe everything starts off with self inside of a Python object. All of the methods do. You would have some other variables if you want, yada yada yada. But more importantly, you have predict. And of course, self is the first argument. Then some x. X will be a list of inputs. Now, pretend we were doing, tumors, and every input has the radius, color, surface area, roughness, temperature, density. That means that one input will have, I'll just make it some values. That's one input. Now another input, we have some other numbers. And another input, we have some other numbers. Well, this whole thing together is X. You pass this all at once to the predict function. The predict function is going to go through every one of these and ignore it. And it's going to output the same prediction for each. But it does have to be aware of them, and I want you to read them in. And if you give it 3 inputs, I want it to give 3 outputs. So it's going to return something. We'll call it Y. Well, if we're always predicting a 1 versus a 0 here, then for this case, Y will be 1, 1, 1. Okay, I'm going to stop there for a second. See if anyone has questions.
Do you want all of our code in that one notebook, or do you want like a separate Python file for like methods?
You can do it either way. I prefer a lot of it to be in the same, but you know what?
Now might be a fun time for you to create your own GitHub project where you put it all on there and then import that into your notebook maybe, or you could just do it in a separate file if you want. But enough of what I need should be visible somehow.
So you want like the whole like predict function and the class and the notebooks.
Yeah. The stuff we're doing, it won't be so hard. You have to build up mountains of code. Okay. So let's talk about another kind of skewed data set. Oh, you have a
I
question?
have a quick question about the homework. I wasn't sure if you were gonna move on to that. Do you care how we like name our folder in the GitHub or like Google Drive?
Yes.
Should it be-
Name it with your first name and last name.
Okay, space. underscore.
Space, capitals. You might want to avoid special characters though. Now, interestingly, you are all going to be able to see each other's code. And there's some notes about this in the syllabus. Now, I want to make this course similar to real life. In real life, we programmers, we see each other's code, we use code snippets, we learn from each other all the time, like several times every day. I'm always doing this. So let's do this here. Now, if you use more than a couple lines, either change it or say I got this from so-and-so. If you use definitely more than 10 lines from somewhere on the internet or someone else, definitely say where you got it, and you have to understand every single line. You have to understand every single line. Now, this means that for your projects to be different, they have to be different in their substance. Even if you use little code snippets of each other, you can't use the same data set. You can't be trying to solve the same exact problem. Does this make sense? All right. Who's heard of information theory? What do you think it is?
I know it's a lot about like trying like a lot of like information loss. And I know entropy is a big part of it.
Yeah.
I remember briefly in the stats class.
Yeah. So there's order and there's entropy. There's a lot of different concepts here. I want to give you an intuition about what entropy is and about what information is. And I need a volunteer. Come on up. You need a chair. I think this chair is too high. You're going to sit here at this table. Sit facing the class. All right. Now, I need you to block your ears and close your eyes. And I'll tell you when, I'll tap you on the shoulder when it's time to unblock your ears. But you keep your eyes closed. Okay, keep your eyes closed. Okay, let's try it again. Okay, now, something you need to know about the pens on your desk is that they are all together. I want you to take a finger and trace around your desk slowly until you find one pen and then stop. You can go faster. All right. Now, where are all the pens? Can you feel them all quickly? Yep. Okay, now I'm gonna do something else. Close your ears again. Okay, now do it again. Okay, now tell me where the other pens are. Yeah, that's right. Okay, you can open your eyes now. Which of those cases strikes you as being one of order and which one is entropy? Yeah, this is entropy. When you come across one pen, it doesn't give you any information at all about the other pens. This is a high entropy state. A low entropy state is when all the pens were together. Okay, you can sit down. What's your name? Michael. Michael, thank you. Everyone give him. So the way we actually calculate entropy is if you have these pens all in a row, we call this a meaningful state where they're all right here, all the pens. Now, I don't care about the order of the pens. So this is the same meaningful state. So how many ways can I reorganize 6 pens such that I have the same meaningful state? Much like, I don't know, 6 factorial maybe, something like that. It's a number, it's kind of a high number. But now think about this. They're all randomly placed. How many ways can I reorganize these pens so that they're still randomly placed? Yeah, a much bigger number. That's the entropy. The entropy of this system is way higher. Now, when it was like this, it still had entropy. And we can still calculate it, but it was a lot less. There's entropy, that's one concept. We now have an intuition. The other concept we need an intuition for is information content. How much information is contained in a message? Now, let's pretend you're living at home here in Spokane, Washington, and you have a connection to a weather tower that's connected to the National Prediction System. And you wake up every morning and you want to know, is it going to be sunny or is it going to be rainy? So 1 if it's sunny, 0 if it's raining. You want to find is today going to be a sunny day? And you get a 1, either a 1 or a 0 every morning, but today you get a 1. Is that really worth 1 bit of information? Or is it something like 0.5? What do you think? What might it be? If you get 1, like a literal number 1 instead of the number 0 in the morning, you know it's going to be sunny. How much have you learned? You learned 1 bit worth. How much?
You know that it's sunny, but from knowing it's sunny, you can just fly.
Oh, that's a good point. Let's not consider implications we know because of a worldview. Let's not consider that. Let's just consider this one thing. How much information is contained in that? One of the questions is, does it matter where you live? If you lived in Seattle, would it be different? Getting a 1 more.
Are we assuming that it's totally reliable?
Yes, 100% reliable. So if you lived in Seattle, you get a 1 in the morning. Would that be more meaningful? Same, doesn't matter.
What's it saying?
Who thinks it's the same and it doesn't matter where you live? Who thinks it matters where you live? Let's pretend you live in Dubai. And you got a 1. Did you learn anything at all? It's sunny every day, all the time. So of course it's going to be a 1. How do you incorporate that? Well, this guy named Claude Shannon came up with a way. Now, as many great things in mathematics go, it's not the only way, but it's just a good enough way that everybody uses now. And it's great. It actually led to so many other great inventions. But this right here is the information content, according to Claude Shannon, contained in a message or an event or a bit. So P, of course, is the probability. And log is just, of course, the log. And we're going to use log base 2. Someone here who has a calculator or some other thing that can do logs or a computer, someone open up their computer or whatever. Who wants to do this? Volunteer to calculate some things for us. All right. So let's pretend we live in Dubai and the probability of it being sunny is 99.9%. And then we get a 1. So the information content in Dubai of a 1 is the negative log of the probability that it's sunny. The probability is 99 or 0.999, something like that. So what is the negative log of 0.999?
0.00004343161.
Or 3, about that?
There's 4 zeros.
4 zeros.
Yeah, about that.
All right. So if you live in Dubai and you get a 1 from the weather tower, it's a bit. You got a whole bit, but it's not worth a bit. It's worth this much of 1 bit. Now, someone look up for me the probability of a sunny day in Seattle. It's not as low as you'd think. What did you find?
41.64%.
All right, that's a sunny day. So put in that number.
Or 6.
Approximate number is fine.
0.38.
What is that?
0.38.
0.38. Still less than 1 bit. That's interesting. Now, if we had, so the negative log, base 2, are you doing base 2?
I don't believe so. I think it's going to be 10.
Okay. Yeah, do base 2.
It's going to be negative 1.63.
It can't be negative. The negative log, the log,
I got you. funny.
So probabilities are always between 0 and 1, right? The log of a number less than 1 is always negative. So if you make the whole thing negative, then you're going to get a positive number.
Probabilities are going between 0 and 1, is it false?
Yes. Yes. I'm going to have you put in some other numbers in a minute.
Okay, I'm just trying to find a calculator that can do it. Like,
Okay, does anyone have Python on their laptop right now?
Oh, Python, but I have another calculator. So -1 base 2 0.464 is 1.107 or 1.108.
So just higher than 1, just more than 1 bit. Now, what if we lived in a place that had a probability of sunshine that was almost never, like 0.01, let's say the rainforest somewhere? What would be the information content in knowing it's going to be a sunny day?
6.64.
6.64. It goes up pretty quick once you get down really low. This is almost worth 7 bits of information. So what is the guiding intuition here? I want someone to tell me in your own words, what is the intuition behind information content?
It's more valuable to know something if it's not common.
Yeah. More valuable to know something if it's surprising. If you live in the rainforest and it's going to be a sunny day, that's very surprising. And some people will apply this kind of stuff to studying stocks. If you know something that's very surprising about a stock, then that could be something good to act on. If you know something important before other people, especially something surprising, then there's more information contained therein. Now, these skewed data sets are going to be a little bit like either this example or this example, and just something I want you to be aware of as we study this. Okay, a dumb predictor. Does everybody have a clear idea of how to do this? It's going to be like a black box. No matter what the inputs are, it always gives the same output, but you do have to process the information, because next week, it won't be a dumb predictor. Next week, you're going to build your first machine learning model that actually does something with real data. And all the other mechanics, you already know, you already have it in place. So it'll be easy. Okay, let's talk about another example from the real world. Speech recognition. When I first started to work in machine learning, this is the field I got into. And I joined a company called Applied Language Technologies, or also known as Alltech, and we called ourselves Altoids. And we probably had a number of real slogans, but our internal slogan was "Talk is cheap, we're not." And we were pretty expensive. We made these phone systems that everybody hates. Call the IRS or Bank of America or Amtrak. You would get our phones. Hello, I'm Julie. How can I help you? They even made fun of us on Saturday Night Live. They didn't use the name Nuance, or Nuance was the company that bought Alltech, but they made fun of some of our products. And one of them, one for Amtrak, really was named Julie. And the voice talent who voiced her, her name really was Julie. I don't know if that was coincidence or if they chose it that way. On Saturday Night Live, the skit went something like this: a voice talent goes on a blind date, and the guy starts asking her questions. She was like, "Hold on," and you hear this little sound. I think you just said, and it has one of these conversations that you probably had with. How many of you have had a conversation with one of these interactive voice responses, IVR. And the first thing everybody tries to do is get around it. Get me to a human, please. And that kind of wore on us at the company, thinking what everyone wants to do with our product is get around it, get away from it, and not use it. But we did our best. Now, speech to text, ASR, automatic speech recognition, they're all kind of the same thing. And supposedly began in 1954. And they use things like formants, where if you take the spectrogram of what someone says, you can find these broad regions which correspond to different vowels. And that was one way to do it. Now, a spectrogram is a good way to do feature engineering for speech. So let's say we have a wave file, WAV, but these are just, it really is the sound wave itself. So it's a pressure differential over time, pressure wave over time. So if like this is our 0 point, then the wave might look like this. And some of you may have used sound editing software and seen these. Who has seen these? Who here knows what a spectrogram is, different from this? Who here knows what a Fourier transform is? Please tell us, and what's your name?
I don't remember exactly what it is, but I could like
It's a conversion to another way of looking at the same data. And this guy named Fourier or Fourier came up with this beautiful mathematical tool that mathematicians use, but computer scientists don't exactly, called the Fourier transform. It involves an integral and a lot of beautiful math. What computer scientists used instead is called the FFT, the fast Fourier transform. And it's done computationally, and it's not perfect. It's a little bit inaccurate, but who cares? It's only a little bit of inaccuracy. What we do is we slice this wave file into time slices. So imagine a bunch of time slices. And then we look in this one time slice and say, what is the frequency, the dominant frequency in that time slice? And you give it a number, like let's say 100. And in this one, maybe it's 200. And this one, maybe it's 137. This one, maybe it's 480. Basically, you get a whole bunch of numbers for each time slice. Now, this graph was amplitude of the sound wave versus time. This other graph, the spectrogram, is going to be frequency over time. Now, you make these time slices very tiny, and each one of them, depending on how you do it, you might end up with multiple different frequencies coming from them if you do some other math. But we end up with, in our spectrogram, let's say for these first few seconds, we had some regions in here that are high frequency and a little bit of low. And then it kind of goes up like this. We can look at when somebody says something, you can see whether it's high frequencies or low or some combination thereof. And they will look like this. So the color indicates the intensity. But what you have there you have these funny things down at the bottom. See these? Probably what's going on here is that one of these is the dominant frequency, and the others are an octave above it, harmonics. And our brain will probably hear this one. But oftentimes when someone speaks or even sings at a given note, there's some dominant frequency you think you hear, but you also hear the harmonics above it. So when you look at this, here's time through some sound file and the frequency here. High frequencies up there, low frequencies down here. When we did speech recognition, we found we needed this and this. We need both. They both give us different ways of looking at the data. Who here has played with any sound software that can do anything like this? What do you do with it?
I mean.
Whale
calls.
Yes. Tell us about the whale call readers that you were working
So we were trying superseded last year. Because there's this into only really identifiable by humans that have access to code to identify them. So we were kind of trying to build a computer, like teach a computer how to identify these calls. So one of the things that we tried to do was build a spectrograms for each recording and then
Very good. So let's pretend instead of a whale call, this is human speech we're looking at. The way we would do this in the old days, before 2004, 6 or so, in the old days, like the late 90s, we would take this file and we would look for places where the energy was lower. And the energy is some function of, these vibrations. And we would posit breaks between phonemes. Now, I mentioned phonemes before. Anyone remember what they are? A phoneme is a bit of a sound of a word. So, like the word F, or the letter F, is going to have just one phoneme. But you might have a W that's going to have a oo and a o. Sometimes there's a couple things in there. Sometimes R's have like more than one actual phoneme in there. But you can take a word like, a word like fish has 4 letters, but really it has 3 phonemes. Fish. So at this one company, Alltech, my job was phoneticist. So I would regularize or normalize all the pronunciations we had in these libraries, the pronunciations of words that we wanted to be able to recognize. And I'll take an example that surprised me was take a word like, Monday. Monday. Everybody thinks they pronounce it Monday. And the phonemes would be something like this. Or sometimes we might write IY was just our phoneme for the E sound for some reason. Monday. We all think we say that. But when you're talking, especially fast with your friends or family, you don't actually say this. This pronunciation did not match many utterances in the real world. What actually matched was that. Monday. Monday matched more than Monday. Monday would match like, 1% of the time, 99% of the time. Monday matched better, but I think I say Monday. We all talk and hear in ways that don't quite match up with reality sometimes. I'm going to play an example for you, and I bet you all know it and will laugh. We hear it. What did you guys hear? How many heard Yanny? How many heard Laurel? Gina, I'm curious what you heard. Okay, so I heard Laurel. Now, the reason that I heard Laurel, and many of you are able to hear Yanni, I'm not able to hear Yanni anymore. Now, some of you guys are probably able to hear both if you think hard enough. I want you to try to hear the other one. Who is able to switch? So, in some ways, it's a little bit like the dress example we talked about, but in other ways, it's also like the Necker cube. Is that cube, is this the front face, or is this the front face? Depending on where you put your attention, are you able to make it flip? Well, with Yanni and Laurel, they're actually both in there. Yanni is spoken mostly in the higher frequencies. The Laurel is spoken mostly in the lower frequencies. And I'm older than you guys, and my hearing is starting to go a little bit. The higher frequencies go first. I can no longer hear Yanni. When this thing first happened, I could almost hear it. I could just barely kind of make it out, like the neck cube flipping back and forth sometimes. And now I have no chance. It's just not there. It's just 100% Laurel from me. You're a little close to me. A little bit.
Actually, that is proof that I.
Yeah, it does. That's right. That's right. So it's harder than you think to figure out what to write so that when someone actually says something in the real world, your ASR system will get that thing. And the Yanni Laurel thing, how do you even write that down? Because they're both happening at the same time and it's the same voice and the same everything. I don't know what speech recognition systems would do to that, but that would be a fun little side project if any of you want to play the Yanni Laurel thing into your phone, into your text thing, and see what it actually says. And if you feel like doing that, do it and send me the results on email, or we can discuss them in class. All right. So the way we did this in the old days is we would estimate the breaks between what we thought probably were contextual parts of phonemes. Now, a phoneme, we already discussed that. We got an I or a sh. Well, for every one of these, we would try to model the beginning of it, the middle of it, and the end of it as separate things. And this would be a little bit different at the end if it was coming before an it. And that it would be a little bit different at the beginning if it came after a. And this it would be a little bit different if it was before a sh than if it was before something else. So for every phoneme, we broke it into 3 parts. Now I'm telling you all this just to give you some history and some context and things to remember. You're not going to have to do this in class. Don't worry, or for homework. So let's say that the part was here. This is the, and then this is the I, and this is the sh. We would have this section, this section, this section, just for the F. And we would take everything, of course, and we make it into the Fourier transforms, you know, with all its lines and harmonics and stuff. And we would map those same regions onto this. So we know, like this is the F, this is the I, and this is the sh. And for this, just one region right here, we have some information. We know which are the prevalent, you know, frequencies, and we can know maybe the density of that region. We can know how intense it is, how in that other picture, how bright they were, how strong is the signal at that frequency. And we can use all this to come up with some numbers. And we can also come up with some numbers from this, looking at the characteristics of that part of the pressure wave. And what we did in the end was we would have, from both sets of places, we would end up with 15 numbers that describes this beginning of the F phoneme. And then 15 more for the middle, 15 more for the end. So you end up with 45 numbers to describe each phoneme. This is how we were doing it back in 1998. So for each of these letters, we get 45 numbers. So as I put in the notes there, we use something about the energy to find these breaks, and then we get 45 dimensions to describe every single phoneme. And these 45 dimensions, it's really just a vector with 45 numbers in it, right? Or a Python list, really, just a list of numbers. That's all it is. And think about that as the input. Now, if you take that 45 length vector, what kind of machine learning model might be good at determining what phoneme it is? You guys know the names of any machine learning models? Neural net. That's what everyone uses now. We weren't using them back then yet because they weren't good enough, but they are the best that we have now. How about linear models? Have you guys heard of linear models? Your first homework assignment will probably be a linear model. And a linear model is basically saying, let's say the output is Y. You could have, you've seen things like this. You're seeing equations like this, right? Well, instead of x squared and x2 and x, let's have them refer to elements in a vector. So x0, x1, x2. So y is going to be some linear function of the elements of the input vector in a simple linear model. Maybe it's double that first field plus 0.3 times the next one plus negative 86 times this one plus 4.2. You learn, or the statistical system learns, to set these numbers so that y is the right answer most of the time, or to maximize the times that y is the right answer. Now, when you do your homework, you're going to have to tell me how often y was the right answer. You're going to have to give me accuracy numbers. Now, accuracy is just simply, the number of right answers over all the answers. But there are other ways we measure accuracy that you're going to have to learn how to code or find it in sklearn, scikit-learn. Who here has heard of scikit-learn? Good. The other ones you should learn from them. You're going to need it. F1 is one of these scores that you will need to give me in the homework, and it's listed on that page. Has anyone heard of F1? Can you give me a little synopsis?
I remember working at the last year, but I'm kind of like, I don't know too much of it.
So we'll pick this up again next time. It's time to end now, but we'll talk about F1. We'll talk about the confusion matrix, and you can start to read about them on your own. Thank you, everybody.
Don't worry about it.